Our first speaker is Roope Uola from the University of Geneva. He's going to talk about quantifying quantum resources with conic programming. And without further ado, I would like to give the talk, the voice to Roope.
Okay, thank you. So I've had a little bit of internet problems, so let's hope that this goes without any interruptions. So yeah, thanks for the introduction, and thanks for the organizers for having me, and also for organizing this online conference. So yes, I'm going to talk about this quantification of quantum resources. The work is a joint work with the people you see on your screens now. And yes, so I'm going to give you a short outline of what I want to tell you. So I'm going to give a very, very short motivation. I'm going to represent the question, this quantification I want to answer. I will do this, of course, what I will need, because I want to quantify something. I want to measure for some quantum entities or quantum properties. So I'm going to discuss two measures for that I will be using throughout the talk. And how will I then use these measures? I will show that they are instances of so-called cone programs or conic programming. And this is a trick with conic programming that I can do, that I can turn an abstract measure into a concrete quantum or non-classical advantage in some task. And I have a bunch of examples. So to motivate and to present the question I want to answer, I'm going to talk throughout this talk basically about non-classical advantages that quantum entities can have. So here, first, of course, we know that for things like Bell locality, steering, and so on, entanglement is necessary. And okay, some other entities could be non-commutativity. That's essential for example, contextuality and other things that are on the screen. But typically in these scenarios, the quantum entity we have is only necessary, but it's not sufficient to gain a quantum advantage. So for example, when we have entanglement, we have Werner states. So we know that there are entangled states which do not violate, say, Bell inequalities. So entanglement is only necessary, but not sufficient for the quantum advantage. Same thing goes with, say, steering and non-commutativity. There are non-commuting measurements which are useless for steering. On the other hand, of course, what we learn when we violate, say, a Bell inequality, we can quantify entanglement in a device-independent way. Also, we can quantify measurement incompatibility from that. So my question here is kind of turn this necessary and sufficient question around, or not even around, or make it sharper. And I will ask this question. Try to find some tasks that would characterize the non-classical entities, such as entanglement or compatibility of measurements, and also quantify this non-classicality. So I want to find really necessary and sufficient conditions in a form of some task that will characterize this quantum entities, such as entanglement. Okay, so how I'm going to do it, this is kind of another outline, more technical one. So I will just take these quantifiers or measures I already mentioned, that I'm going to use two of these. These are for non-classicality or for the quantumness of some entity, such as this could be an entanglement measure, for example. I want to turn them first into something that looks like a witness. This I will do with these cone programs. And these witnesses I can then turn into tasks. So witnesses, I mean, they're implementable, so they always relate to some sort of task. These tasks turn out to be quite nice, actually, in this case of these measures I choose. And this will give us the main result of the work. So the abstract quantifiers, I said I have two, so I will just go straight to them. One is the so-called generalized robustness. This just means how much some quantum entities entanglement can take mixing before it becomes separable or classical. The other one is the convex weight, or okay, best classical approximation, best separable approximation. This kind of free fraction is also a name for this one. Okay, they don't say too much as such, but I will give the definition and I have a figure of both. So here first is the generalized robustness. And I hope you can see my cursor on the screen. So in the picture, the outer set is the set of all what I call devices. So now a device can be anything. It can be a quantum state, it can be a state update, it can be a quantum measurement, it can be a set of measurements, a quantum channel, even a process matrix if you wish. So now, here's the set of all devices, and within it is always a classical set, which then could be, for example, the case of states, this could be separable states, or in case of measurements, this could be those that are compatible. So or I would have tuples of measurements. These could be the compatible ones. These could be states which have no coherence if devices were states and so on. Point is that I first fix the type of device, and then I draw the space, and then I choose a free set. Only point of the free set that is important here is that it's convex, but that's only a technicality. Now, I take point of interest D, device D, say it could be an entangled state, and I take another device, could be a state also here, E, and I draw a line between them. Now, I ask how far can I go from this point D towards point E before I hit the free set. So in other words, I lose the quantum resource. So from entangled state, I would mix with another entangled state, I would become separable. And now this, how much I can mix, how much this D tolerates this kind of mixing, this is a quantifier. This is the noise tolerance of D with respect to this set F. And okay, more technically, it's written here down. So the robustness, there is a subindex F, just means that with respect to the set, classical set F, is the minimum number such that this left-hand side quantity here is in the free set. So this left-hand side quantity is nothing but the point on the line between D and E. This is just another way of parameterizing convex combination of D and E. Okay, so that's rather abstract looking, but I will show that it actually turns out to something very concrete. As another measure, so this is noise tolerance. The other measure looks exactly the same, only difference is that my E went here to the right-hand side. So now I just try to put D into a convex decomposition of something that is for free, would be a separable state, and something that is here on the set of all devices E. And now I ask for the best possible points D, F, and E, so that I will minimize this quantities fraction of this E, or in other words, I will maximize the quantity of this free device D. So this also explains the term that the best classical or best free approximation or best separable approximation, because I have the biggest weight to optimize this quantity over DF and E, I have the biggest weight on this free device here for the optimal point DF and lambda. So those are the two measures I will show that have actually an operational meaning. So I will take the robustness here and show how, because like I said before, that my trick is to, also it's in the title, my trick is to have such quantifiers or measures as instances of a cone program or conic program. So I need cones. This is rather simple. How do I build a cone from here? This is the robustness optimization problem. I take this 1 plus t, multiply it to the other side, and define a new quantity d tilde f. So this d tilde f, of course, if this df is in the set f, this d tilde f is in the cone that is spanned by spanned by f. So the cone spanned by a set is just that I take the set and I multiply it with the positive real line. So this d tilde f is always the cone spanned by set f if this df is in f. So now I can have something that looks like a cone, a conic constraint in my optimization. Also, this takes care of some nonlinearity because you see in the optimization there would be t over t and e over t, both of which I optimize. So that takes care of the nonlinearity. There's another small technical thing. I can solve the t times e. And with this, I can rewrite my optimization as follows. It becomes, the optimization constraints become conic or semi-definite constraints. But the point is that there's no linearities anymore, and I have the cone constraint I want. So I can explain this right-hand side of this optimization. What do I mean by the trace d tilde f? So if you look at the trace of that, it is 1 plus t times trace of df. Trace of df depends on the type of device, what it is, so I will just label it as nd. It's a constant. When I fix the device, it's a constant. In case of states, it's 1. In case of say, POVMs, it's the dimension of the space. In case of channels, it's the trace of the choice state. So it's 1. So this is just a constant that depends on the chosen type of device. So now you see here's a constraint. D tilde is in a cone, and d tilde f minus d is positive. Why this? This just guarantees that E is also a device, and as you see, now I have gotten rid of T and E in my optimization. I only have D tilde left. It envelopes all the constraints from here on T, E, and DF. It takes care. I only optimize over 1 variable. In this lower one amounts to the fact that I optimize over 3 ones here. So it's kind of nice formulation. I can do the same thing for the weight. I'm not going to show the calculation because it's as simple as this one. I just write the conic constraint like this. This 1 minus lambda times df is my new guy. So it's again, d hat f is in the cone that is spanned by the set f, and I have a conic optimization problem. So as I have written here, these are instances of conic programming. So now, why did I want to make them conic programs? It is because I wanted to get the witness that I mentioned earlier. So witness is something measurable. I can interpret that as some kind of a task. So how to do that? These are conic programs. So in other words, they are of this form. Conic programs are typically of this type of form. So we have some linear operator lambda. So that is now operating on operators, basically it's operating on matrices. I maximize some sort of inner product. This is just the trace or Hilbert-Smith inner product. X is my variable. So here are some constraints. This inequality is a matrix inequality. In general, it could be a cone inequality, but it's not. And this is a cone inequality. What's a cone inequality? It only means that X is positive in the cone if it belongs to the cone. So it's just a short way, another way of writing that X belongs to the cone. Sounds maybe a bit weird, but this comes with a Lagrangian dual, and then this kind of cone inequality makes more sense. So this, how to get from this kind of optimization to its dual form is just by using Lagrange multipliers. And the resulting optimization problem is this one. So this variable X changes to a variable Y, to a so-called dual variable. And we get, so Y here is positive, whereas X was cone positive. And now here is this looking inequality. What does this mean? It only means that lambda deca Y minus A belongs to the dual cone of C. Dual cone is just those points which have positive inner product with everything in the cone. Now this is a really strong result, this Lagrangian duality here. So it says that these two problems have the same optimal value if so-called Slater's conditions hold. Slater's conditions hold in all the examples I will give. They are rather weak. They basically say that there's an inner point, or there's a point where this inequality is somewhat strict, so there's no equality, to kind of inner point in them with respect to that inequality. So because the sets, the classical sets we consider are so simple, so nicely behaved, this will always hold. These two problems are the same. Now using this, I had a cone program. How to get the witness for it is using this duality. So I can now write my robustness. It was a cone program in a much nicer way. You see all the cone constraints, all the cone inequalities disappeared. So then my robustness reads like something looks like there would be a witness in it. So if you read it carefully, I want to maximize, so device D, I want to maximize its inner product with some operator W, which is positive, and has this property that its inner product with any point from the free set or the classical set is less than 1. So of course, if with this W, this maximization, I find W such that this value here is more than 1, that how much is more than 1 is the robustness basically, or if it's the optimal point of this optimization, this W. So this is a witness. You could think about an entanglement witness. They look the same. Sometimes they just say that, okay, it's Hermitian instead of being positive, and the inner product has to be either positive or negative for separable states. But it's the same thing. One can scale these things. One nice thing for me in what I'm going to show is, or what I will need is that this witness is indeed positive. That will help a big deal when I try to formulate this witness as a task. Okay, same thing holds for the weight. I can take the Lagrangian dual of that one, and I get another inequality which looks, optimization problem looks like a witness. So weight, they somehow, I want to minimize now the inner product, where in the robustness I want to maximize. Again, I have positive witnesses which have such property in the free set, so the inner product is larger than 1 in the free set. Okay, so this is the dual formulation. And now, this is the important part, that the W, the witness, is a positive operator because it can be then implemented in many ways. So for example, when my devices are measurements, this W, I can easily write it as some sort of state. I can interpret it as states because I can just renormalize the W, the witness, into a state and multiply it then with the corresponding factors. So I will get in the end for measurements this dual of the conic program will correspond to a state discrimination task, because W is the task, it's the states I want to discriminate, and measurements are my strategy. So my device is a strategy in that discrimination task. For states, W can be interpreted as a phase discrimination task or subchannel discrimination task. Here the trick is that I take the spectral decomposition of W and just normalize it into something that is a POVM and a subchannel discrimination or a phase, adding a phase, so basically unitary. And then this is my setup. So I have the added phases and I have the measurements after that is W, and states are my strategy. What states should I put into this protocol in order to get a good discrimination probability for my even phases? For maps, this relates to some sort of collaborative, some sort of game where W, this witness, says that, okay, which states I send into my map and what kind of measurements I perform after the map. And the map is the strategy. So I want to find a map so that I kind of maximize my output or my payoff in such a game. I will not go into these details. It's rather simple how to put this W into such tasks, but it's also a little bit technical. I don't want to go into details on that more than I have already done. Okay, in quantum games, the thing is that they are maps, so we have to do everything in joy picture, but then we use, in technical terms, the operator Schmidt decomposition for W. Okay, with all this, so I took two abstract measures, made them into conic programs, took the dual, and now I know that these witnesses can be implemented as some sort of tasks. Just by decomposing them in a nice way, I will get the main result of the work, which is rather general and a bit long, but I will go in detail through here. So here is the main thing. This is the part for the robustness. So we fix a type of device. This could be states, measurements, channels. This could be sets of states, sets of measurements, sets of channels. This could be even process matrices and processes. This could be quantum instruments or state updates. Now we take a convex subset of devices of this type, and this compactness is not too important because we can always close, for with finite dimensions, we can always close the set, so that is not important. Convexity is important. So now any device which is not in this subset, you can think about Fs, for example, as separable states. Any subset, any device that is not in this subset, for that I can find a discrimination task so that this D performs better than any member in F. So if I had an entangled state, the statement would be that, okay, for that entangled state, there is a discrimination task in which the entangled state performs better than any separable state. Okay, but we get a bit more with this thing that we put the quantifiers in. So this outperformance, we have the following formula for it, how it's quantified. And I will explain this. Okay, right-hand side is just robustness, but left-hand side, on the top, we have this success probability in the discrimination task for device D, and the task is in task T. So this is basically the witness we have. I've just put it into a task form, into states or measurements, or whatever we'll need to put it, depending on the type of device we have chosen. When we take this success probability and we divide it in the same task T with the best success probability that 3 objects, so for example, separable states can have in that task, optimizing this quantity over all possible tasks of this type that we have now chosen, so for example, state discrimination or quantum game, we will get exactly this robustness, or 1 plus robustness. So in other words, every quantum resource, when this free set is convex, this F is convex, can outperform every classical counterpart, every point from F, and the outperformance is exactly quantified by this robustness measure. As another result, I have the exact, or it's not the exact, but exactly the same looking thing for weight. But before I go there, I want to mention one thing. This kind of result as I have here, this appeared for many, many separate sets F in the literature, in the case of states originally. So for example, for steering, and it appeared for asymmetry and coherence, for example. And of course, that somewhat, but that's quite much motivated us also to look into this problem. Also, this was proven for when the device type is a state in general, also in the literature before our work. And but okay, we see it's a very general connection. Now let's take the next slide, which is for weight, for which this kind of results did not exist. In that there was one before we did this one, and but it didn't exist in that, or there were not as many cases analyzed. But of course, having this kind of general formalism, we figured that, okay, it works also for this weight. So only thing that will change the next theorem is discrimination will become exclusion task. So here is the same result for weight. So once again, fix the type of device, and all the same, take a device outside of this set F. And now we said there is an exclusion task in which D strictly outperforms all members of F. And the weight is the exact quantifier of this kind of outperformance in exclusion tasks. Or if it's a quantum gain, then it's minimizing the payoff in the game, whereas for robustness, it was maximizing. So this is kind of interesting to see that this works also for the other quantifier. And this would be interesting to see, of course, in the future that are these just instances of some way broader thing, because weight and robustness in a way are two ends of the same family of entropies. One can see them also like this min and max entropy, or they relate strongly to those. So maybe there's some way of finding a more general result. See that these are just instances of that. That is something for future work. Okay, so now I just have a few examples left. So those are just basically recapping what was in the literature. So as you have seen, this is rather general result. So, okay, on measurements, one can have something. This is just examples of the free set one could choose. The simulability, informativeness. Okay, simulability just means that I try to simulate one measurement with using, say, sharp measurements or binary measurements and so on. Informativeness means how far am I from a coin flip POV, which only is identity times a probability distribution. Sets of measurements, there's joint measurability. There's also a form of simulability there, joint measurability being a special instance. Okay, and these all appeared in the literature, some of them at the same time as our work. On states, as I said, many things were known: Schmidt number, coherence, asymmetry, entanglement. Also, in general, all the state resources for robustness were known. State assemblages were known. The steering, similar thing was known there. There's something else, Schmidt number interoperability. If you want to know, I can tell more about that later. But there's also, I want to point out here, a paper also in the last one was Dukuara. These were for weight. So others here are for robustness. For CP maps, okay, one could have applications there. I think interesting one are entanglement breaking channels, because they can somehow be seen also as quantum memories, or a model of those. Okay, instruments, there are quite some. I want to just mention non-classical teleportation, that in this paper, the people did a little bit different than we, this game strategy, or this was slightly different. So if you look at there, it's not exactly the same as here, but in similar spirit, the results nonetheless. For thermodynamics, we just took a few random examples just to show the broadness of the result. So thermal operations are something one would consider as free. True quantum decoherence is one possibility. So unital channels that are not random unitary. And in measurement theory, there would be incompatibility of channels. That was also in a few other papers mentioned. So to conclude, what we did was that we took these rather abstract looking measures, as you might now remember the pictures I draw and how the optimization looked, and they turn into measurable quantities with these tricks from conic programming. So this gives...
You have 1 minute left, including questions.
So okay, so I will wrap up here. Okay, please. Yes. So okay, so we got this task in the characterization and this channels to higher dynamics, so I didn't talk too much about those. Thank you.
Thanks, Roope, for this talk. We have less than one minute for a question. If somebody has a question, it's time to ask now. I don't see any questions in slide though. I would like to ask you, Roope, could you describe a bit more what is the task T in your main result? How is the task defined in terms of your set, convex set that you consider classical?
Yes, exactly. So if let's say that I have, for example, POVMs would be my set of, my type of device. So this T, it would be different states and samples that I try to discriminate with my POVM. So when I optimize over tasks, with POVMs, I would optimize over state discrimination tasks. So different states that I send to my POVMs, or different state and samples.
Thank you very much. I would like to remind people that they can ask questions in Slack in the channel of this session if they have more questions about the talk. And with this, I would like to change to our next speaker. Thank you, Roope.
Thank you.